For forces, we've mostly looked at Newton's second law. Newton's second law says that basically F equals ma is the equation, although the version that we use is A equals F over m. These are identical. It's just a rearrangement, because if we take F equals ma and divide both sides by m algebraically, we get A equals F over m. We use this equation a lot. Don't forget it. Newton's second law, in words, is basically the two patterns. The words are basically the acceleration and net force are linearly related. We learned that in the force lab. As the force increases, the acceleration increases in a linear way. Acceleration versus mass. When the mass increases, the acceleration goes down. Heavier things are harder to move. I always think about this in terms of football. The linemen, the biggest guys on the field, they are trying not to be moved, and then so they need to be bigger. And then the cornerbacks and the wide receivers who have to do a lot of running are much thinner. They've got to be easier to move so that they can accelerate. So linear inverse, this is basically the description of Newton's second law, which is that force equals mass times acceleration. Force and acceleration are linearly related. Mass and acceleration are inversely related. So when we are solving these problems, we're just going to use this equation, a mass of 10 kilograms, same strategy as the motion, right? 10 kg is the mass, net force is the F, 2 newtons. What is the resulting acceleration? So A equals F over m. So that equals, maybe I should do it out here, A equals F over m. And we're going to plug it in now. We've got our F of 2 over our m of 10. You got to be very careful with this because your instinct is usually to put the bigger number on top. I've seen that a lot. But we gotta, that's why it's always best to write it down first. A equals F over m, and then we put our F in for our F and our m in for our m. So this is, you could say 1/5 or 0.2, and our units for acceleration are meters per second squared. Now, I'm okay with it if you want to say, okay, 2 newtons divided by 10 kilograms and put the units as 0.2 newtons per kilogram. That's fine with me. A newton is a complicated equation, but basically newtons divided by kilograms is meters per second squared. But let's not get into that. All right, so a constant net force of 20 newtons. This is where you got to be careful with this word constant. If it's a constant speed, there's no net force. But a constant net force just means the net force is 20. We don't really need the word constant unless the force was changing. So we've got a net force of 20, a mass of 5 kilograms, A equals F over m. And so we take our net force of 20 divided by our 5, and we get 4 meters per second squared. All right, so for number 28, it's a two-part problem. 2 kilogram block, maximum of 2 newtons of force, and pulling on it when 10 newtons of force are applied. So when we pull on something with 10 newtons of force, but 2 newtons of friction are resisting it, friction is always a resisting force, then our net force, which means total, equals 8 newtons, because we take the 10 minus the 2. So that's the resulting net force. And now we need acceleration equals F over m equals 8, right? Our net force. We don't care about how much force we're pulling on it if there's some resistant force. We need our net force when we're calculating acceleration. 8 divided by 2. So 4 meters per second squared. It's acceleration units. Down here, we always do the same idea. Only one force, only one force. One force, one force. Adding up these forces is a little bit more complicated. We've got 6 to the right, and then 2 to the left, minus 2, and then we add them up. So a total of 4. Over here, we've got minus 3 to the left, and plus 0.5 to the right. So if we add these up, we get negative 2.5. And this one, I messed up. This needs to be negative 2 newtons. 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 Do not forget your units on the test. I'll be mad. And if it's going to the left, we're calling that negative, and to the right is positive. Then our accelerations are always F divided by m equals 1 in this case, 3 over 3. 1 in this case, 3 over 3. I almost forgot the units again. In this case, though, you might get tripped up because it doesn't matter which way we do 2 divided by 2. Oh, and this is -1. Man, these are common mistakes for you to make. If I'm making them, I'm sure you might as well, so watch yourself. F over m equals 4 over 8. Don't get trapped here. It's force divided by mass, even though this is the equation. 4 over 8 equals 1/2 meters per second squared. And then this one is even more complicated, -2.5 over 6, which is more complicated number, -2.5 divided by 6, -0.42, from a round properly, meters per second squared. Sorry for the bit of sloppiness there. All right, so going back to our distance versus time and velocity versus time graphs number 22, label each situation as balanced, unbalanced, speeding up, or unbalanced, slowing down. Forces working in the same direction as motion when we're speeding up, forces working in the opposite direction of motion when we're slowing down. So we'll flip back over here real quick, number 22. Constant velocity forward. If it's constant velocity, the forces gotta be balanced. That's what constant means. Constant velocity means constant speed. Acceleration means change in speed. And if we're going to have balanced forces, we've got to have no net force. Our forces have to be balanced out. Think of it as a person on a tightrope, walking along on a tightrope. As long as they're balanced, there's no net force. They're moving steadily, they're not accelerating. But as soon as they come unbalanced, they start to fall. That's an unbalanced force. So both constant velocities, balanced, balanced. And if we were looking at these graphs, balanced, balanced, no acceleration. As soon as you've got acceleration, and this is speeding up, right? So if you can label things as ASU, you can label it as unbalanced, speeding up. And slowing down, unbalanced, slowing down. At rest, balanced. So if you can do these, and you just remember that balanced forces, sum of the forces, net force equals 0, constant speed for balanced forces, then you're most of the way there. And you'll need that somewhere else on this as well. All right, so do different sized objects feel the same force of gravity? Do different sized objects experience different accelerations because of gravity? Now, this first part is not something we've talked about very much. But force of gravity is mass times acceleration. F equals ma. And specifically force of gravity, it's F equals m times the acceleration due to gravity, which is the same for all objects. So do different sized objects feel the same force of gravity? No. They actually feel different forces of gravity. Do different sized objects experience different accelerations because of gravity? Also, no. Which is a little confusing with the phrasing. So, here's an example. Galileo took his bowling ball and his apple up to the top of the Leaning Tower of Pisa. And he dropped them both at the same time. And they hit the ground at the same time because they had the same acceleration. So, why do they have the same acceleration? Well, it all comes down to this Newton's second law idea. If we have F equals ma, and we have a large object that is 50 kilograms, let's say, well, its force due to gravity is going to be 50 times 10, which is the acceleration due to gravity, 500. And if we have a very small object, its force due to gravity is going to be, let's say it has 5 kilograms, 10. Its force of gravity would be 50 newtons, 500 newtons. So very different forces of gravity. But if they're affecting different masses, they're going to get the same acceleration. So 500 newtons of gravity force on a 50 kilogram object leaves us with only 10 acceleration. 5 kilograms with 50 newtons on it, also 10. Okay, so that's maybe unnecessarily confusing, but the idea is that acceleration is the same, but the force of gravity is not. All right, so talking about skydiving now, jumping out of planes. Does the force of gravity on you change as you fall? Big no. The force of gravity doesn't change anywhere on this planet. All we can do is do other forces that counteract it, but the force of gravity itself stays the same. So our acceleration, does that change? Yes, because of air resistance. Because as we fall, the air, we have to claw through more, we have to fly through more and more air every second. And so the air resistance increases the longer that we fall. And we reach a maximum speed because of that air resistance. The net force is 0 because the force down equals the force up. So when we're drawing this, I'm going to start off drawing the force of gravity on all of these because that's the simplest. And I'm going to draw it the same size each time because force of gravity doesn't change. It stays the same everywhere on this planet. You'd have to go to the moon or another planet to change your force of gravity. Then let's look at the other forces. So when we're still at the plane, the forces must be balanced. We're just flying in the plane. Planes fly at constant speeds. The forces are balanced. So we've got to have a force up that's the same size as the force of gravity. Normal force is the force that comes from surfaces. Anytime you press on a surface, it's the normal force pressing back. And same size. When we jump out, is there any more normal force? No, we just jumped off of it. So there's no more normal force, and there's no other force at all. Now, I wouldn't fault you if you put a small force of air resistance, but really, air resistance doesn't come until you're moving very quickly. Like terminal velocity. We just talked about this. We reach maximum speed called terminal velocity because the forces are balanced. The net force is 0. So now we need an upward force that's the same size as the force of gravity, but this one is the force of air resistance. When we pull the parachute, our air resistance gets bigger. This is the maximum the air resistance can be because we're not going to go any faster anymore. But when we pull the parachute, we catch a whole bunch more air resistance, so it's got a much bigger force of air resistance. That's why we slow down. We don't ever move upward, right? We accelerate upward, but we're going so fast downward that it slows us down. So then at some point, I didn't put this step in here, but at some point we'll hit terminal velocity again as we slow down, and then we'll float with the parachute equaling the force of gravity, equaling the force of air resistance. I didn't put that step here though. Then when we land, we're moving quickly down and we're gonna stop, which means we need a big normal force, bigger than the force of gravity. All right, we're almost there. Let's look at this graph here, this little grid. Always, if you see a grid like this, use the grid to take the grid. So like looking at this row might help you a lot because this row I've filled in the numbers for you. No acceleration, no net force, negative 500 some other force, 500 force due to gravity. So what situation is this with no acceleration? This is terminal velocity. Constant speed. So now let's go back up to the top and maybe we can look at this a little bit better. So still in the plane just before the jump, we're not accelerating yet. We can't go straight to the normal force necessarily unless you're super ahead of the game. But if you kind of jump over here and think, okay, what's the acceleration going to be if I haven't jumped yet? Well, it's going to be 0. What's the net force going to be? If the acceleration is 0, the net force is 0 every time. They don't match up otherwise because you have to involve the mass. So what does my normal force have to be to make my net force 0? Well, it's got to be the opposite of the force of gravity and the same amount. That makes 0, 0. See, it's exactly the same as this line. And hint that that line's going to be on here one more time. So when I jump out, does my force of gravity change? No, there's nowhere on this planet I can go to change my force of gravity. Do I have any more normal force? No, I just left the normal force behind by stepping out of the plane. I don't have any air resistance yet. How do I know that? My net force is 500. So if my force due to gravity is 500 and there was any force here, it would make the net force something other than 500. So this one's got to be 0, 2. So then how do I solve for acceleration? A equals F over m. I told you it would come up again. So we take our force, 500, divided by our mass. Where are we going to find that? In the problem. Mass is usually hiding in the problem. So this is 10 for the acceleration. We don't have to put units in a chart because they're right here, meters per second squared. All right, so terminal velocity, constant speed. What is this force that's resisting me? The force of air resistance. Shortly after opening the parachute, has my force of gravity changed? No, it's never going to change. Can't go anywhere and change the force of gravity, but I can change my net force by changing the other forces on me. So shortly after opening the parachute, I've got a force of air resistance. And with the parachute open, I've got a force of air resistance. Shortly after opening it, if my net force is negative 200, what does my air resistance have to be to make 500 happen? So you can kind of do a little algebra here. You say 500 plus x equals negative 200. What do I need to put here to get to negative 200? So if you did the algebra, you'd be subtract 500 from both sides. X equals negative 700. Gets me to negative 200. And then acceleration equals F over m. So 200 divided by 50, which is negative 4, because it's negative 200. So my acceleration is negative here. This is an equal sign. I know my handwriting is a little sloppy. This is a positive. We're accelerating down, and then when we accelerate negative, we're accelerating up. Are we moving up? No. In the whole time of skydiving, you never move up, but you slow down, and that's what that negative indicates. So then, moving at constant speed, there's your key. If you ever see constant speed, we can jump straight to acceleration and put a 0 there. Net force, 0. Air resistance got to be negative 500. Told you it would come up again. This line is here 3 times, although the skydiving is not going to be on the test. So when I hit the ground, if my acceleration is negative 6, well, to find the acceleration, I divided the force by the mass. So to get back to the force, I multiply by the mass. And that's F equals ma, if you want to use that. So F equals 50 times negative 6. So my force has got to be negative 300. So again, I would do this. 500 plus x equals negative 300. It's got to be 800. And this time it's the normal force that's working against me. All right, so this is a free body diagram for a 3 kilogram box being pushed along, moving at constant speed. So draw the free body diagram. I gotta have 4 forces on here. Because it's sliding, it's moving along, it's got gravity, it's got a force of push, and it's got some friction, because it's got to. So my force of gravity has to equal my normal force. I drew these the same size. And then the force of my push has to equal my force of friction. If it's moving at constant speed, all the forces have to be balanced. They've got to look like this. So what would the net force be? 0. Acceleration, 0. Force of friction? Well, if it's pushed with 5, force of friction must be negative 5. So that's forces.